Well, here we go again, and we are moving into a very practical part of chemistry, and that is the idea of electron configurations. And we've just come out of quantum numbers, and really electron configurations are the application of quantum numbers. So let us begin here. Consider the neutral hydrogen atom. And what is its ground state electron configuration? Okay, I think we need to understand some things about electron configuration. So here we go. Electron configurations. Good. So I guess the place I always like to start, you guys should know this by now, is with a definition, right? Definition. What is an electron configuration? It is a representation of the arrangement of electrons in an atom. That's what I would say. That's what I would say electron configurations are. Good. Now, what's kind of cool about this, as I said, is that this is really a application. To me, this is an application, a practical application of quantum numbers. Quantum numbers. Because remember we said, hey, with quantum numbers, what were we trying to do? We were trying to figure out the energy level, the shape, and the orientation of an orbital, right? As well as the spin of the electron. So when I take these guys all together, you know what we get? We end up getting an electron configuration. Good. So that's kind of our definition. And there's three ways we kind of represent electron configuration. So let's write down types here. And one type will be what I call electron configuration notation. Electron configuration notation. Electron configuration notation. And that's the first one we want to talk about. We'll talk about a little shortcut later called the noble gas method. Noble gas method. And then another interesting way to represent the electrons in an atom is what's called orbital notation. Orbital notation. Okay? Good. So those are the three types. We'll get into the other two a little later. We're going to start off right here with an electron configuration. Now, electron configuration notation takes the general form of, let's say, what? NL to the number, okay? Something like 3p2. Now, what does that mean? N is our energy level. Hey, cool. Energy level. And L would be what? That represents the shape of the orbital or orbitals, and then the number is the number of electrons in the set of orbitals, right? What do we call a set of orbitals? We call that what? A subshell. So 3p2 would mean what? I'm at the third energy level, the third N. P means what? I have a p-shaped orbital. And 2 means I have 2 electrons in this p-shaped orbital. Got it? Hey, great. Now, one last thing up here off of electron configurations is we need a set of rules. There are some rules, okay? And rule number 1, we'll start right here. Rule number 1 is called the Aufbau Principle, a good old German word, Aufbauen. Aufbau Principle. And it states that electrons fill or enter, occupy, you might say, orbitals of lowest energy first. Okay, Well, how do we translate that? Remember, we said we could be at certain energy levels, like n equals 1, n equals 2, and n equals 3, right? And we said those represented an energy, right? That when I'm at n equal 1, that is a lower energy than at n equals 2, and n equals 2 is a lower energy than n equals 3. So when we apply our Aufbau principle, it says electrons want to go into n equals 1 before they go into n equals 2 or 3. All right, I think we can do our first consider. What is the ground state electron configuration for the hydrogen atom? And we're talking about electron configuration notation here, not orbital notation or any of the others. So first, we have to figure out how many electrons hydrogen has. And to do that, let's go to the periodic table. Here's hydrogen. Hydrogen has 1 there. 1 meaning what? Oops, let's move that arrow. 1 means what? 1 proton, but if it's a neutral atom, that means it has 1 electron. So that means I have 1 electron to place. And where is that going to go? It's going to go into the lowest energy level. So that means n equals 1. So I'm going to put a 1. But what shape? Oh, man, I almost forgot. Let's go back and let's consider our quantum numbers. Remember, we have n, and I have s, L, and I have m, and I have s, right? And when my n is equal to 1, remember n is 1, 2, 3, 4, 5. What are my L? Well, I'm going to go from 0 to n minus 1. So when n is 1, L is what? 1 minus 1 is 0, 0, 0. Good. Does that mean there's no orbital? No, it doesn't. Remember, when L is equal to 0, what kind of shape do I have? I have an S. When n equals 1, I have a P. When L equals 1, when L equals 2, I have a D. When L equals 3, I have an F. Good. So I have an S orbital here, right? And how many orientations of that do I have? I have a 0, meaning 1 orientation, and I have plus 1/2 and minus 1/2, right? And so this is my first shell. Good. All right, I think we can answer our question now. I go where? I go to the 1s, and how many electrons do I place there? 1, and so my electron configuration for hydrogen is 1s1. Moving on, consider the neutral helium atom. Okay, helium. Where's helium? Here's helium. How many electrons does it have? Well, it has 2 protons, so when it's neutral, it has 2 electrons. All right, so I have 2 electrons that I need to place, and where am I going to start? I'm going to start with what? I'm going to start at my 1s. Now, I have an s. Let's go back here, right? I have an s. How many orbitals do I have if I have an s? I have 1 orbital. This is the number of orbs, remember? I have 1 s orbital. How many p's do I have? Well, I have 3 p's. How many d's do I have? I have 5. And how many f's? 7. So if I have 1 s orbital, I do have an s orbital, right? Here's my s orbital. It has 1 orientation. How many electrons can fit there? 2. So can I say 1s2 for my helium? Yes, I can. I can say 1s2. Great. And that would be my helium because that says I have an energy level is 1, that my shape is an S, meaning it's a sphere, and how many electrons do I have there? 2. Oh, great. That's exactly what we have. Next, consider lithium. Okay, where's lithium? Lithium, right here, folks, over here. Here's lithium. How many electrons does it have? It has 3. So we want to place 3 electrons, and where are we going to start? We're going to start where? 1s, and how many we'll put in there? 3, right? No, 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 no. We have another rule. Here comes the second rule. Second rule. This is over with rules. Number 2. Number 2, rule number 2. It's called and you guys know him well now, the Pauli Exclusion Principle. principle, right? This is the second rule for electron configurations. There can be no more than 2 electrons per orbital, each with opposite spin. Okay, so there can only be 2 electrons per orbital. And so when I go with my lithium, I can't put 3 here because how many S's do I have at the one level? Let's go back and look. At the one level, I have one S orbital. It can only hold 2 electrons. Do I have any more orbitals in the one? The answer is no. That means I have to go to the second energy level. And what are my L's for the second energy level? Well, 0 and 1. What are my orientations for the 2, 0? I have a 0, 2 electrons off of that orientation, 1/2 minus 1/2. Now, how many orientations do I have off of the 1? Well, I have 3, a -1, a 0, and a +1 orientation. Each of these could hold 2 electrons because each orientation represents an orbital, right? And this would be S. This is when L is equal to 1. What do I have? L equals 1. That means I have a P orbital, so this would be a P. And this would represent like a P, some kind of maybe a PX. This might represent a PZ or a PY. And this would represent a PZ, right? The P orbital in 3 different orientations in space. Okay, so I could get what? 2 electrons here, and I can get 1, 2, 3, 4, 5, 6 here. Good. Okay, I think I'm starting to understand something here. So I can't do this, but what can I do? I go 1s, 2, and then I go to what? My second level. Now, when I go to the second level, I have 2 choices, don't I? I can go to my s orbital, or I can go to my p orbital. Well, this goes back to our Aufbau Principle. Okay, what we have to understand is, let me put a little star here because my orbitals actually have different energies. So let's come over here and let's talk about my orbital energies. Orbital energies. Good. And there's really, let's talk about relative energies. At any level, so at any energy level, we have this arrangement for orbital energies. S have less energy than P's. P's have less energy than D's. D's have less energy than F's. F's less than G's, and so forth. So that would mean at any energy level, meaning at any n. So like the 5s orbital is less energy than the 5p. The 5p has less than the 5d. The 5d has less than the 5s, and so forth. Okay, so now when we apply our Aufbau principle, it says my electron wants to enter at a given level, the s first. After the s is filled, then it enters the p's. So here we are, right? We have 2 options. First, we're going to do this and go into the S's. After the S's are filled, meaning they both have their electrons enter with different spins. Then, after that, we'll go to the 2 P's. So, I think we can answer this now. Where do we go? Not the 2 P's, we go to the 2 S's. How many electrons? So I have 2 here already. I need to have a 3 total, so 1. So this is my lithium electron configuration. 1s2, 2s1, meaning I have 2 electrons in my first energy level in a sphere-shaped orbital, and then I go to my second energy level, and I have 1 electron in a sphere at that energy level. Okay, good. Let's move on. Consider the neutral beryllium atom. You guys can do this one. Pause me, and when you're done, I'll tell you the answer. Well, let's see. How many electrons does beryllium have? You go to the periodic table. Beryllium has 4 electrons. Good. So that means I need to place 4 electrons. Where's my first one going to go? It's going to go into the 1s. And at that 1s orbital, how many electrons fit there? 2. And then where do I go? I go to the 2 energy level. What orbital shape? S, or what subshell we could say, right? How many can fit there? 2. So now I have 2 there and 2 there. That equals 4. How many do I need to put in? 4, or account for 4. So this would be my beryllium. 1s2, 2s2. Good, 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 good. There we go. How are we doing on time? Let's see. Okay. Let me see. Let me see if we want to do the next one or if we want to call it here. What's the next one? Neutral boron. I'll tell you what. Let's call it quits right here, and next time we'll hop to boron. Okay. Thanks for your attention. See you next time.